What's up, guys? All right. So, day two here. 721. Taylor just tested positive, so now both my kids got it. Life is good. Anyways, we're rolling. So, sampling distribution of p hat. So we're really getting into the thick of it now. We'll use this a lot as far as inference goes, confidence intervals, all that stuff. So, what's p hat? Let's say we go out into GHS. We take a sample of 100 kids, and we want to know the proportion of people that have broken a bone. And we get a sample that the first sample number one, we get 40 out of 100, so zero point 0.4, and then we do it again, right? Sample number two. There's going to be sampling variability, right? So we go back out, we take a new sample of 100 kids, and then we say how many have broken a bone, and maybe this time, 42 out of 100 or 0.42. And so we continue this process a bunch, and let's do it, 100 times. And then what we'll do, right, is we go and we do a distribution of p hat. P hat is all of these samples, right? So we go and we have zero point 0.2, zero point 0.3, 0.4, 0.5, 0.6, and we start keeping track of all of the results that we get. And then we use that information to try to figure out what do we know about the actual proportion, right? The population proportion. Okay. So we're just going to get into some basics here. This is actually a really quick lesson. You're going to choose an SRS and you're going to take a bunch of different proportions and you're going to graph them all. The mean of that distribution, right? Remember, we're going to graph this thing. The mean is going to be just equal to P, okay? And then we have a standard deviation right here, standard deviation of this distribution, and it's equal to this formula, the square root that's given to you. It's on your formula sheet, so you'll always have access to that, as long as your 10% condition is good to go. And what will this thing look like? You can see how I drew it. It's symmetric. It will be normal if these two conditions happen, right? Which we checked before. Okay, so let's kind of jump in and see what this looks like. So you've got National Center for Educational Statistics, 20% of students who recently earned a bachelor's degree were business majors. So they tell us, right? They told us the actual population proportion. Okay, imagine taking a simple random sample of 300 students who recently earned a bachelor's degree and calculating p hat, which is the proportion of students in the sample who majored in business. Identify the mean of the sampling distribution. So from right up above, the mean, which is mu, of this sampling distribution is just equal to P, which is the population proportion, which they gave us right from the beginning. So it's 0.2. Okay. What about the standard deviation of this distribution? By formula, it's P times 1 minus P over N, which is the square root of 0.2. 1 minus 0.2 is 0.8, divided by, we took a sample of 300. And so when you come in your calculator, second square root, again, you can do your fraction, alpha y equals enter, and you've got 0.2 times 0.8 divided by, 300, and you get 0.023 equals 0.023. Okay, but remember, that only works if the 10% condition is met. So what's the 10% condition? The formula that we use, remember, is that we want the population needs to be greater than or equal to 10 times the sample. And this is guaranteeing independence. Okay. And so how do I know? Well, population greater than or equal to 10 times 300. Population greater than or equal to 3,000. So you're supposed to ask yourself that question. It says, students who recently earned bachelor's degrees. Do you think that the population of all students in the United States who earned bachelor degrees is bigger than 3,000? Yes. So you can just say, assume that there are greater than or equal to 3,000 U.S. students with a BA. Okay, so you just write that. Yes, I can assume that the population is bigger than 3,000. Okay, cool. And you guys know, right? This is stats class. Once you have a mean and a standard deviation, that sounds like we can calculate stuff. And we can. We can use that normal CDF thing. But as a reminder, when you go in here, you can't click that normal thing unless you know that your distribution is normal. And so how do you check that? You check it right here. As long as these two things happen, you can assume that the distribution is normal. So you have to check what is n times p, that is the sample size of 300, times p, which was 0.2. 20% would be 60. And then what is, that's greater than or equal to 10, check. What about n times 1 minus p? Well, that's 300 times 0.8. And 80% of 300 is 240. That's definitely bigger than or equal to 10. And so now we can say, therefore, or thus, we can assume distribution of p hat is approximately normal. Okay. All right, so you go out into the world, you take a bunch of samples. That's going to be a distribution of p hat. We can calculate mean and standard deviation, and we can check for normality. And if all of those things happen, you guys know the drill. We can go in here and calculate certain things that give us answers to a question like we're going to do next. Okay. All right, so flip your page over. This is the last one. It's just one problem here. And we're going to do basically the same thing, but once we get a mean and a standard deviation, we're going to be able to calculate something. Okay, so in 2016, more than 200,000 students took the AP Stats exam. Of these students, 14% earned a score of 5. Find the probability that a random sample of students who took the 2016 stats exam would indicate that 15% or higher scored a 5. Okay, so we have population proportion given. So you can just kind of write down what we got. We know P is 0.14. Okay, there are more than 200,000 students that took the exam. Find the probability that a random sample size 300. So my sample is size 300. Okay, find the probability that this sample is greater than 0.15. So what's the probability that p hat, right? The proportion of your sample, that's why I dressed it up. This is population, this is a sample, is greater than 15% or higher. So greater than or equal to 0.15. Okay. And hopefully, you know, this kind of looks familiar. What's the probability? Well, look, you could do this if I could just go hit that normal CDF. And if I had a mean and a standard deviation, I could just put it in and we're done. And so that's what we're going to find. Okay. So for the distribution of p hat, we know that the mean of p hat is just equal to p. We know that the standard deviation of p hat is equal to the square root of p times 1 minus p over n, which is the square root of 0.14 times 0.86 over n, which was 300. And we type that guy in. And we say, let's quit out of here. Second square root alpha y equals enter. Let's do 0.14 times 0.86, all divided by 300, and we get 0.02. Okay. Now, you can only use that standard deviation if you check your 10% condition. Right? What is that? Is the population greater than or equal to 10 times the sample size, which is 3,000? And we can say yes, right? How do I know that? Because it told us more than 200,000 took the AP Stats exam. So it's definitely clear that you're good there. Okay, now, normality condition. How do we check that? We do n times p, which is 300 times 0.14, which would be 30 plus another 12 or 42. And then n times 1 minus p would be 300 times 0.86. 300 minus 42 is 258. Use your calculator, that's fine. Are these both greater than or equal to 10? Yes. So we, therefore, 3 dots, assume approximately normal. Okay. And you guys, what we just did, right, is we went out and we took a bunch of samples. We didn't actually do that, but that's what the math is telling us would happen. If we went out and we took a sample size 300 over and over and over again, we would get a distribution with a mean equal to 0.14 and a standard deviation equal to 0.02. Okay. And if we want to know this question, right, what's the probability that p hat is greater than or equal to 0.15? Well, 0.15 is right here. All we want to know is what's the probability that that happens. So we say, well, that's normal CDF from 0.15 up to massive number, call it 10,000, with a mean of 0.14 and a standard deviation of 0.02. Label your stuff. This is lower, upper, mean, standard deviation, and we're done. We come in here, second distribution, normal CDF, 0.15, massive number, and then 0.14, 0.02, and 0.31. So there's roughly a 31% chance that, assuming this is true, if it is true that that 14% earned a 5, there's a 30% chance if you go randomly select 300 kids and you ask them, hey, raise your hand if you got a 5, and you count them all up, what percentage would have a 5 or more? That would happen around 30% of the time. It's more likely that you would not get more than 15% who would raise their hand for a 5. Okay? If it was our class, of course, but we can't stack the deck. All right, guys, we'll keep rolling. Hang in there.